unimolecular means say one molecule, but we'll discuss it in the gas phase, and this is a typical problem because in the gas phase, molecules, even a single reactant molecules, if you take, it may decompose and they will react among themselves. So at least two molecules should be involved according to collision theory before a reaction should start. But interestingly, the overall reaction would be unimolecular. So how we can explain that reaction mechanism, right? On the basis of observed kinetic study, we can theoretically formulate to its kinetics, right? That is differential rate law. And it is very interesting that it requires some simple model, and we will again consider the collision theory, of course. Without using the collision theory, this cannot be explained, but there is a concept or a model that should be introduced, and it was actually proposed by Lindemann, right, a scientist. He proposed this model, and interestingly, using this simple model, one can explain the experimental findings regarding this rate law. So that we'll discuss today first. And if sufficient time is there, then we'll discuss reversible reactions a bit. Okay. So now I'll present that kinetics. Okay. This is unimolecular reaction and collision theory. Collision theory in a closed container, if you keep the two different molecules, then they will react normally. They will collide among themselves and form some product. But here, in the simplified model, we will propose a reaction scheme like this. So Lindemann proposed this reaction mechanism in 1922, right? And the mechanism he proposed that we consider here in a simple elucidation like this. It involves three steps, right? Here we represent A as a reactant molecule, any particular reactant species, like that. So in the first step, two molecules of reactants are involved in 1:1 stoichiometry ratio, and it forms A plus A star. Superscript star indicates what? Activated molecules. That means in equation 1 we see two molecules, they will not reacting because no new chemical products are formed. Rather, out of these two reactant molecules, you please switch off your video. Hey, sorry, unmute, please, mute, please. Your speaker, please mute. So A plus A to A plus A star means, suppose in a closed container, you take a gaseous reactant species A, and two molecules will collide. After collision, one of the molecules get energized, right? So it is written as A plus A star. It is an activated molecule. Now in the subsequent step, step 2, this activated molecule will react with normal molecule present in the reaction vessel to produce 2A. That means this is the step where the reverse reaction occurs, means reverse step. The energized molecule come down to the বলো। হ্যাঁ, পাঠিয়ে দিয়েছি সকালে। তোমার ওই পার্সোনাল মেল প্লাস ইনস্টিটিউটে প্লাস ওই পুপল লিঙ্কটা তো পাঠিয়েছি হটমেলে। Now, this in the third step, so basically the first and two constitute a reversible activation and deactivation step. The forward reaction A plus A to A plus A star we call activation step, and the revert step, that is A star and A, will revert to the normal molecules reactant species to A plus A, that is to A, with different rate constant K2. So naturally, two reversible steps, that is activation and deactivation, they occur at different rates as indicated by the respective rate constants, right? K1 and K2. The third step, that is a crucial step, means here the activated species decomposes to produce a desired product B and C with rate constant K3. Okay. Now we'll discuss this before discussing going to the kinetics. We'll just propose the actually what we consider, how we consider this mechanism. That is a very important. Suppose the two molecules, they can collide, right? And after collision, what happens? One molecule may get energized, means activated, means at higher energy. And there may be a time lag between the moment of activation and the moment of decomposition. Suppose A star, once it is produced, it has to pass to, it can proceed into two channels, separate channels. One is A star either can revert to its the initial state, or that is deactivation step we call, or it may decompose to produce the desired product B and C. So the activated species can proceed either to the reaction channel, or it may revert to its initial state. This is very important. And another thing is that once a molecule is activated, it requires certain time for the decomposition, because you know that it requires to cross an energy barrier for a certain reaction, right? So naturally it requires some certain time. Okay. Now these activated species within this time lag may collide with another molecules, reactant species present in the reaction vessel to and be deactivated. So the energy activated molecule, reactant molecule, may react as in the third step, but it may has also an opportunity to collide with other molecules, or it may collide with the reaction vessel for deactivation. Okay. So this is the unimolecular gas phase reactions that we are considering. Now, so this is the mechanism, that is, it involves three steps as I written already, and I am writing the corresponding rate equations. You follow carefully. The first step, which is the activation step, so we write the rate of formation of this energized or activated species, that is given by K1 square, because we are considering that it is a single step, so naturally unimolecular, and since two molecules are involved, so it seems to be second order. Now, In the subsequent step, that is deactivation step, A and A star reacts back to produce A. So since the concentration of activated species decreases, so we put a negative sign and we write the rate equation, differential rate equation as given here. Now, in the final step, what is the rate of the reaction? This is very important. Minus d A star concentration of A star dt equal to dB dt equal to dC dt, because B and C, these products are produced in 1:1 stoichiometry ratio. So naturally, as in the unique rate law representation, as we had discussed earlier at the very beginning, so we can write the unique rate law, differential rate law, either in terms of the reactant or products like this, right? Since all are present in 1:1 stoichiometry ratio, so that stoichiometric factor does not appear in these expressions. And this overall rate of the equation, we can write simply K3 star. Okay. Now, what is the fate of A star? Means activated molecules or energized reactants molecule. It is normally a short-lived species. Means this activated molecule cannot exist for longer time. Why? Because it has surrounding normal molecules. So many molecules it has, they are colliding, they may collide with these activated molecules. Or activated molecules even may collide with the container wall inside, right? So there are several ways these activated species have a chance to be deactivated, right? Because of collisions either with normal reactant molecules or with the container of the reaction vessel. So at any time, concentration of this activated species, as in the steady state approximation, as you know, that concentration would be very small. Okay. And because this is the rate, that is rate of formation of a star and rate of decomposition of a star. Right. Decomposition means in the sense not only reaction, disappearance. That is better we should write down instead of decomposition, because decomposition means a single step, that is reaction. Not only that, rate of formation is this equal to rate of decomposition of a star, and another term that we should write, that is, okay, that we write, okay, another term that we should write, that is rate of deactivation. The total rate of disappearance, which basically this total rate, that is rate of decomposition, right, through third step or rate of deactivation. These two steps together constitute what we call rate of disappearance of A star. And at the steady state, this must be fulfilled. So naturally, you can write rate of formation of A star is given by this expression. Rate of deactivation given by this expression. And third term that appears in the right hand side denotes the rate of decompositions to get the products B and C. So based on the steady state approximation, one can easily find the concentration of this activated species, that is A star. It is given by simple expressions like this. This is very interesting. Now, as you know, that overall rate of the equation, it is given by K3 star, that is third step. And in the third step, this activated species A star will be replaced by the expression in the right hand side here. Just we put the expression and get and simplified expressions, rate equation like this. Now, this interesting rate equation, if I ask you what is the rate, what is the order of the reaction with respect to reactant, it is very difficult to get an answer because you see the reactant concentration of reactant species appear both in the numerator and the denominator. So cannot be it cannot be answered in a straightforward way. What should be the overall order of the reaction because of the uh, explicit expression of this rate equation. Okay. Now we consider two cases. Suppose since steps 2 and 3 they are competing with each other. That is deactivation and rate of decompositions. They are two competitive process. Right. Both the process consumes the activated species. Now, if we say rate of deactivation is much larger compared to third step, the decomposition step, then what would happen? Then we can write, that means when the situation will arise, that you should know first. When we say the rate of deactivation process would be much greater than rate of decomposition step. So deactivation means A star plus A equal to 2A. When the process is larger or sorry, when the pressure, because in the gas this reaction takes place in the gas phase, when the pressure is larger or concentration of A is larger, then what happens? Suppose when the concentration of A is larger, then the activated species will have a greater chance of colliding with normal molecules for deactivation. Right. This is the case. When the pressure P is larger or concentration of A is larger. This is very important. Okay. If the pressure of the reaction species in the vessel, if the pressure P is large or concentration, whatever you can say, because we can write P and C like this, N by V, because this is equal to, at a given temperature, P proportional to C when T is kept constant. So that's why both P and C are identical of species. So if it is kept larger, then the deactivation step will be much larger than decomposition step. And this can be simplified to this simple expressions. Now let us consider the denominator. Yes, denominator. There we see the factor K2A as K3. Since K3 is small, we can ignore the second term in the denominator and we can write K1, K3 by K2A. Yes. So this is the ultimate rate equation under this restriction. What is the restriction? The rate of deactivation is much larger than rate of decomposition. And when this situation arises, when the pressure or the concentration of A is larger in the reaction pressure. And we see the overall rate equation seems to be a first order. Okay. Now case 2. There is another case, how to simplify the overall rate equation as proposed by Lindemann. Right. Here we say that here we assume that rate of decomposition is much larger compared to the rate of deactivation. This is very important. There is product, there is activated species move to the product channel with a greater ease compared to its deactivation step. And naturally, that inequality that Harry proposed, K3 will be much larger than K2. Now, when this approximation could be valid, or how we can justify this approximation, that is why how we can suppress the deactivation step and enhance the decomposition step. This would be possible provided if we maintain the reaction mixture at lower gas pressure. So if there is a lower gas pressure or lower concentration of reactant species, then the chance of collision of the activated molecules with normal molecules will be much less. So that should have a sufficient time lag of the activated species to move towards the product channel. That means decomposition step will be favored. And naturally, under this restriction, that is K3 is much larger than K2A, and so in the denominator we can easily approximate, we can modify it, and we get an expression like this. It is very straightforward. If you find the overall rate equation, yes, yeah, and then if we put K3 is much larger than K2A at lower, particularly at lower pressure, then we can write the reaction overall rate is appears to be second order. Right. This is very interesting. So it appears to be second order. So that means these unimolecular decomposition reactions, may either follow a first order kinetics or second order kinetics. It depends only on the concentration of the reactant species, right? And accordingly, the two competing process one can monitor, that is control, that is either product channel or the deactivation channel. These two competing process could be controlled by changing the pressure of the reaction mixture. Now, do you have any confusion or any query right now? Hello?
No,
Do you
sir.
have any question? Or do you need any clarification further? Hello?
Sir, I have a question.
Please explain the case 2.
Yes, what happens? I cannot hear you properly, please.
Sir, please repeat the case 2.
Yes, in the case 2, if we keep the concentration of reactant species very low, that means if the pressure of the reaction vessel we maintained at lower pressure, at lower region, right? So that means the activated species cannot easily collide with its surrounding molecules, right? Because of the lower concentrations, because density is less. And in that case, we can expect that the activated species will have a greater chance for decompositions, that is reaction channel, it can proceed rather than deactivation. So that's why under this restriction we say K3 term factor will be in the denominator, K3 would be much larger than K2A. Okay, and if you put this restriction in the original or the initial expression, rate equation, overall rate equation here, then from this expression you can easily write down this R equal to K1 square. So this is the second order reactions. So that
So
means
how does
from
deactivation occurs?
deactivation, what
Yes,
you
sir.
mean? Are you attending this class right now or just you join now? Tell me
No, sir.
frankly.
I have joined from the beginning.
Then what's the problem? Then what is the problem? Just you please tell
Sir,
me. No, no. You just tell me. Uh, what are the three steps of the reaction? You first tell me.
sir,
What
one
are
is activation, one is deactivation, another is decomposition.
right? It's very simple. Now, why it is difficult for you to follow? I cannot
No, sir.
answer.
How does deactivation occurs?
You see, what is the step two? Deactivation means what? Deactivation
Uh,
means what? Suppose two reactant molecules A and A, they collide and one of the molecule is energized, means energized to higher level, means it gets higher energy, right? And this we call activated molecule. These activated molecules, may all the molecules, reactant molecules are not activated, right? So that should be threshold energy when we call it is activated. Energized means suppose two molecules collide and some energy may be exchanged and one may get lower energy and another will be at somewhat higher energy. But whenever we are talking about activation, means it must have sufficient energy, and that sufficient energy, or we call that is at a certain energy level. So once we have an activated molecules, it is ready to either decompose, right? Or it can mutually collide with neighboring other molecules, normal molecules, which are not activated at all. And after this collision, again that energy may be dispersed. Means that energy will be lowering. That is the energy level of that activated species will be in the ground state, right? By releasing the excess energy. So this is the way of deactivation. Either it
okay, sir.
can collide with the reaction vessel or it can react with also reactant species. But if your density or the concentration of the reactant species is very small, then once the molecules are energized or activated, then it will have a lesser chance, much lesser chance to be deactivation, right? And in
Yes,
that
sir.
case, we can write like this. So this is the approximation. This is nothing so complicated. Okay.
Yes, sir.
Now I can give you some uh, practical example. The thermal decomposition of azomethane. Right. Azomethane is a chemical species, as you know, a formula, right? CH2N2. Now, thermal decomposition of azomethane, uh, we can write that expressions that we obtain like this, right? From the rate equation that original that we derived, that we have rewritten like this. Okay, that expression, simply these expressions, we have these expressions, this we have written in this form. If we divide that numerator, that one of the A concentration term, we can write it in this form. Now suppose A is larger, then what happens? If you look at the right hand side, if concentration of A or the pressure of A is much larger, then what happens? In the right hand side, can we write K1, K3 by K2? This ratio is simply constant because these factors are at constants which depends only on temperature. So it is a constant quantity. Now we see what happens at lower concentration. When A is small, then we can ignore in the denominator K2A factor. And naturally it becomes this. That is a that concentration becomes this. So if you write the rate equation in this form, there's nothing else. Same thing we have written in this form. Okay. Now if we plot, because azomethane when decomposes, it produces nitrogen gas, and azomethane itself also a nitrogen gas. So naturally, instead of total pressure, we consider the partial pressure denoted by Pi. Okay. And this rate equation that is in this form, that is 1 by Pi dP dt, if we plot against pressure, partial pressure of azomethane, then we see a plot like this. Initially, it increases steeply, and then the rate slightly increases or remains constant or parallel to this pressure axis. Okay. So that means the kinetics of the decomposition of azomethane perfectly follow this rate equation. That is the indirect proof of this model or the mechanism as proposed by Lindemann. Okay. So this is an experimentally plotted curve for this decomposition of azomethane. And what we see, the straight line with a arrow shown here. Can you guess what should be the order? Can you remember? What does it indicate? Just initially, the tangent that we draw here. What does it mean? Can you guess?
Zero order.
Yes.
Zero order, C naught by
Yes.
2K.
Yes. If we written in this form, just like it is constant, right? Just linear. You see, K1 is. So that's why you get this plot at lower concentration region. At lower regime of pressure, you see, it is a straight line. But at higher pressure, at larger pressure, we see the rate becomes constant. That expression should be a constant quantity, asymptotically constant or parallel to this pressure axis. So this is a nice demonstration, practical demonstration of this reaction, that is mechanism, that is Lindemann hypothesis, and how it confirms the experimental observation. Okay. Now we will discuss the reversible reaction. Okay. Reversible. And I think you have some idea, that is from these expressions, what you can say, this is a reversible reaction. Reversible in the sense A to B and B to A, both are possible. Actually, almost all the reactions all are reversible in nature, but it depending on the reaction difference in the rate of the forward and backward. Sometimes it appears that the reaction appears to be unidirectional, but it is not correct. Okay. When it appears particularly in precipitation type of reactions, that is ionic reactions, when you add silver nitrate to barium chloride solution, then it appears to be as if almost all the product, that is silver chloride, is precipitated at once, and the reactions is almost completed. This kind of reactions we see almost completed, but actually once silver chloride is formed, it will have a tendency to decompose into the respective ions, silver ion and chloride ion. Although the reverse step is very small. That rate is very small, right? So that's why this category of reactions, as you know, we call reactions which are almost completing in nature. That is very important. Okay. So now just we consider simple reversible reactions where both forward and backward step follow first order kinetics. And here A is the initial concentration of reactant and XE denotes the equilibrium concentration. Right, E denotes equilibrium. And forward rate constant is denoted by K1 and the backward is K subscript -1. And this is the rate equation. Can we write this equation? Can we write these expressions? How can we write? Say at equilibrium, first you look, can we write this equation? You just see, can we write this equation or not? You just carefully note.
Yes, sir.
Yes, sir.
Yes,
Yes, sir.
sir.
Hello, sorry for disruption. And any query, please? Hello.
Yes, sir.
So at
No, sir.
equilibrium, what we are writing? Can we write like this? K1 A minus XC equal to K minus 1 XC?
Yes, sir.
Yes, okay.
Yes, sir.
Because
Yes,
yes,
sir.
both are first order reactions, so you can write like this at equilibrium. Now, from this expression, you can simplify and write down these expressions because what is capital KE here? Small k1 by these are the rate constants, and this capital KE here, E stands for equilibrium constant. As we write the concentration of B by concentration of A at equilibrium, we can write like this. So KE denotes equilibrium constant. Here KE is equilibrium constant. Okay. Now, what is the rate of formation of B? Dx dt equal to this, and dx dt equal to k1 a minus x minus, now look, instead of k minus 1, we put these expressions. K1 a minus x is these expressions, we put it here, right? And we just manipulate the right hand side and get an expressions like this. Okay. So this is the rate equation. And if we integrate it, then put an integration constant C, and we can write from the formula of integration, we can readily write down in the left hand side minus xc. ln means log e base, natural logarithm, minus k1 at plus c. Now, as we put some boundary condition or restriction to find the constant c, here also we put, as usual in the reaction cases, t at time t equal to 0, that is initial time, there is no formation of product B. So x equal to 0. Okay. And we can write C equal to this minus xc ln xc, because xc is equilibrium concentration. It is independent of time t, right? Okay. So we can write k1 at equal to, just simplify. You put the concentration A, you put the constant C, and manipulate it, right, to get these expressions. xc ln xc by this, or t equal to this, t equal to this, right? This is very interesting. And once again, it is an interesting fact that at equilibrium, when a reaction reaches at equilibrium, then only that concentration of the product, of course, should be much larger than x. Otherwise, the time t would be a negative quantity. It cannot be possible. So this restriction that at equilibrium, the concentration or mole numbers of reactant A of product B, that is Xc, should be much larger than X. What is X? X is the concentration of B at any time. Right. So at equilibrium, concentration must always be greater than the concentration of the product at any other time. Right. So otherwise, from this expression, it appears to be that T should be negative. Since it cannot be true, that means Xc must be greater than X. So this is very interesting. The question is, which is larger, Xc or X? The answer is definitely equilibrium concentration of the product must always be greater than its concentration at any time, right, before reaching the equilibrium. Okay. If you have any question right now, it is a simple illustration and simple manipulation it involves. You can read yourself. Now, how to evaluate K1? Because after the reaction is over, we can get the product concentration, which is the equilibrium concentration Xc, and you just measure the amount of B at different time intervals, T1, T2, like that. So, and you plot ln Xc by Xc minus X versus T, right? That is this quantity. We are plotting ln Xc by Xc minus X versus T, right? And from that, you can get a linear relation like this, because A1T, A is a constant quantity, Xc is also a constant quantity. So if you plot this particular quantity, if you plot versus time t, then what we get from the slope? What we get? Can you guess? What is the slope? What is the slope?
AK1 by XC.
What is the slope?
K1A by XE.
We are plotting ln this versus kt k1t, right? So the slope would be equal to a by x. Since x is known, because at the end of the reaction,
Sir,
that
A
means
K1.
x, sorry, k1. So you know the equilibrium, initial concentration of A, you know the equilibrium concentration xc, so you can easily find out from the slope, right? So once you know
Sir,
k1, yes,
sir, the slope would be A K1 by XC.
yes, sorry, the whole term, right, k1t, it would be simply A by xc. I've written, is all right, it's all right.
Sir, why not K1 is included in the slope?
No, we are plotting t, na? Oh, okay. I thought that it is plotted k1t like that. Okay, it's all right, you are all right. AK1
Okay, sir.
by XC. I thought it is plotted like this K1T. Okay. So you know this A and XC, so you can find out K1 from the slope. Okay. So this is the way you can, once you get K1, now you can also find out the reverse rate constant from these expressions. That is, you come here. Yes, from these expressions. Because you know this one, you know this one, so you can find out. Okay, so both k1 and k minus 1 can be evaluated. Once you know k and k minus 1, you can find out k equilibrium constant. So what we get from this study, that we can calculate, one can sorry, one can calculate rate constants k1, k minus 1, and equilibrium constant of the reversible reactions. Right? From this kinetic study, one can measure all these quantities. And what we have learned, that xc is always greater than x. That is, equilibrium concentration of the product must always be is the highest, right? So if you allow sufficient time or longer time, that means the reaction will gradually settles down to an equilibrium state, and at the equilibrium state you will get the maximum amount of product, right? Okay, that's all.
Yes, sir.
Yes, so you follow these kinetics. If you have any confusion, you can ask any question right now. Okay, so thank you all.
Thank you, sir.
Thank you, sir.
Sir, I have a question.
Yes, you can raise any question. Any question?
Sir, without any external
Yes,
power in equation 1, where the two molecule collide and form an A molecule and an excited, how is this
yes,
possible, sir?
not
Can you explain
excited.
more?
No, it is not excited. It is an energized molecule or activated molecules. Activated in the sense
Sir.
that it has sufficient energy to decompose. Right. That means,
Yes, sir.
energization means it can have any amount of energy, but that amount of energy is not sufficient for a chemical reactions. As you know, it requires certain minimum amount of energy that we call activation period or activation energy, right? So activated molecules can pass to the product or decompose, means it acquires that minimum amount of energy that is called, what is that? Activation energy, right? That's why you call it is activated species. Okay. Hello. Do you have any other query or any question? Please.
No, sir.
Okay. Thank you.
No, sir.
Thank you for attending this class. And you give your attendance in the chat box. That will control regularly. Okay. Okay.
Okay, sir.
Thank you all.
बेस्ट टीचर है यहाँ सर।
सर चलेगा बे
हाँ,
फिटनेस करा दे रहा फिर तक
हम
पूरा
लोग को दे
लेक्चर
रहा
छोड़ दिया।
अटेंडेंस।
अब सूर्यश को पसंद आ गया है सर।